Hey guys, it's Mr. Lowry. This is the lesson for 12-2 if you're in A cohort for Wednesday. If you're in B cohort, this will be for 12-3, which will be on Thursday. Today we talked about arithmetic sequences. So this is actually your book, and I'm going to go through a little bit of this with you and also give you some of the things we kind of talked about in class. But this section is actually really good. If you go through this section in the book and read through it, I think it will help you a lot with learning how to do what we call arithmetic sequences. So this starts on page 200. It's section 4.6. And let's talk about that word a little bit for just a second. This word right here, it looks like the word arithmetic. And you can say it like that. Arithmetic is a noun, and it's the name of a type of math. So we have like arithmetic, which is usually plus, minus, multiply, divide, the kind of math that you learn when you're a kid in elementary school. And then we got algebra, which you start learning, in 7th, 8th, 9th grade, and then geometry and things like that. So that word you might have heard of. When we use this word to describe a sequence, we say it arithmetic. So when this word is a noun, we say arithmetic, and it's a type of math. When we use it to describe sequences, we say arithmetic. Kind of weird, but that's kind of how it is. So there's some important key concepts in here. We'll zoom in here. Now, you will probably want to pull this up online, your online book, because you won't be able to see this very well. But there's a bunch of key terms where it talks about term and sequence and arithmetic sequence and what that is and common difference. Those are all really important ideas that I'm going to talk about in just a second. And then there's also this idea, this core concept. This has an equation for an arithmetic sequence. This is an important idea as well. So if you need some extra reference material since you're missing class and maybe don't have as much, this is a great section to go through and read through and try to do the examples so that you maybe understand a little bit better about sequences. Okay, so I'm going to put this aside for now, and I'm going to kind of go through some of the notes that I gave in class that are similar, but kind of building on what we've been talking about. Okay, we're going to start with what a sequence is. Okay, a sequence is just an ordered list of numbers. So here's some examples of some sequences. Now, if you pay attention and you look closely, you might actually recognize these from the pattern task that we did, right? So this activity that we did was kind of getting us started on patterns, and we know that, in this pattern here, this has 5 tiles, and then this has 9 tiles, and then this has 13 tiles. And the pattern that we found is, it's adding 4 every time. The next one has 17 tiles, right? So I just kind of use these as examples as sequences. So this is a sequence, 5, 9, 13, 17. And the pattern here is that it's an add 4 pattern. This is actually the sequence for pattern 2. This is that doubling sequence, right? 2 doubles to 4, 4 doubles to 8, 8 doubles to 16, and so on. This is that second pattern from this representing patterns task. This guy right here. 2, 4, 8, 16, 32. This is just represented in like a sequence form. And this is the last one. This is pattern 3. This is the one where we have like the square with the extra pieces on it. This guy right here. So we had 5, and then this one had 8, and then this one had 13, and then the next one had 20, and the one after that had 29, right? And each of these has a different pattern. So a sequence doesn't have to have a specific pattern. It usually will have some kind of pattern. Not always, but most of the time they do. And these are 3 examples. So this is kind of like a linear sequence. It adds the same number every time. Plus 4, plus 4, plus 4, plus 4. We see that kind of constant rate of change there. This one right here is more of what we call an exponential pattern because it's doubling, right? So if you've ever heard of exponential growth, that's what's happening here. 2, 4, 8, 16, 32. Then it goes 64, 128, right? So this gets big pretty fast. Okay, this one has a squared in it, and if you remember the formula that we came up with this one, it was n squared plus 4. And this is part of the quadratic family. Last week we talked about function families. And sequences have a lot to do with functions. They're kind of related. And so we can kind of put these in a family for the kind of pattern: linear pattern, exponential pattern, quadratic pattern. Okay, so that's a sequence. Sequences, like I said just a minute ago, are very similar to functions. They have an input, they have an output, and they have their own notation. So I'm going to go over sequence notation, and if you are familiar with function notation, this isn't quite as hard. So in a sequence, here's my sequence, right? This is the one from above, so I'm taking this sequence, talking about this guy. These numbers here are called terms. So those are the terms of the sequence. Okay, now what we don't see is we don't see the figure number. In our pattern here, our pattern task, going back to this first pattern task, we had figure 1, figure 2, figure 3, figure 4. Right? That piece we don't see in a sequence. So we have, it's an ordered list, so they have a position, right? Position 1, position 2, 3, 4, and 5. But this is typically hidden. We don't see this part. But we just know from looking at the sequence, this is the first one, the second one, third one, fourth one, fifth one. So first term is in position 1, second term is in position 2, third term is in position 3. Now, if you count these numbers down here, these are like our inputs and outputs here. When we graphed our patterns here, that we did in the last activity, we used the step number or the figure number as the input, and we used the number of tiles as the output. So in a sequence is like a function, but the inputs are usually invisible. They're just the position that they're in. Okay, and we use n for that, just like we did in the pattern task. N was like the figure number or the step number. And then for sequences, we say a n or a sub n or a of n. So our input is the position number. We call that n, where we use n for that variable. The output is the term, and we use a sub n, or a with a little n underneath it. And that's kind of like using x and f of x, right? This is input, this is output. For a function, for a sequence, it's n and a sub n or a of n. So let's do a couple examples, and let's look at some notation here. If you see this, you would say this a1 or a sub 1 or a of 1. All of those would be okay. A lot of times we just say a1. What this means is this guy right here, that little 1, is telling you the position number. Okay, so a sub 1 is asking you what term is in position 1, or we sometimes say that's the first term. So you're like, okay, cool, here's position 1. What number is in position 1? It's 5. So for this sequence, we would say a sub 1 or a of 1 or a1 is equal to 5. A4 then is asking you for the fourth term, or the term in position 4. So we got 1, 2, 3, 4. Okay, there it is. There's the number in position 4, or the fourth term. Okay, so here's a new sequence, and we want to find A3. What does that mean? It means find the number in position 3, or find the third term. So 1, 2, 3. There it is. So A3 or A sub 3 or A of 3 is equal to 8. So very similar to functions, it's just that the inputs you can't see. We just count 1, 2, 3, 4, 5, right? We could write a little, 1, 2, 3, 4, but we don't really need to because it's an ordered list. We already know that it's in the order that it needs to be in. Okay. Let's talk about arithmetic sequences for a second. Okay, I've said that word before, and a lot of times, students get confused, like, wait, isn't that word arithmetic? Again, when we're talking about sequences, we use it as like an adjective, and we say arithmetic. But it's okay, it doesn't really matter how you say it. But an arithmetic sequence is basically like a linear pattern. Okay, arithmetic is the word we use for linear in the sequence world. Now, linear means line, right? And in sequences, you don't really have a line, so you have to use a different word, and we use arithmetic. All right, so if we look back at our original examples here, we got a linear, an exponential, and a quadratic. We actually use different words to describe that same pattern in sequences. So instead of saying linear, we would actually call this an arithmetic sequence. Okay, there's actually another word for this one as well. Instead of saying exponential, which refers to an actual function or a graph, in sequences we call this geometric. Okay, today we're going to focus mainly on these arithmetic, and then next semester we talk more about these geometric sequences. Okay, so arithmetic is a linear pattern. We talked about this pattern here was like a +4, +4, +4, +4 pattern. Okay, so we're adding the same number over and over and over. All right, so arithmetic sequences. An arithmetic sequence is like a linear function. So these terms are similar. Okay, similar idea. A linear function has a constant rate of change, and that's like a slope, right? You see like that straight slope, constant rate of change. This is the wording we use when we're talking about functions or graphs. Constant rate of change. In a sequence, we use a little bit different language, but it's the same idea, and we say that an arithmetic sequence has a common difference. Okay, the variable that we use to represent common difference is d for difference. So we're basically looking for a linear pattern, and we're looking for the constant rate of change. We just don't use those words. We use the words arithmetic and common difference. So let's look at an example that's similar to what you got on your homework. Okay, determine if the sequence is arithmetic. Is it linear? Does it have that constant rate of change? If so, find d, the common difference, or like the slope, basically. Okay, so let's look for patterns here. So 2, 7, 12, 17. Are we adding the same thing every time? Well, this is like a +5. To get from 2 to 7, that would be a +5. To get from 7 to 12, that would be like a +5 as well. 12 to 17, that's a +5. Okay, so yeah, this is adding 5 every single time. That's basically a linear idea. So is it arithmetic? Yeah, it's arithmetic. So we're going to write arithmetic. Sorry, it's a little cramped here. That's for this guy. All right, if so, what's the common difference? Okay, it's 5, right? We're adding 5 every single time. So we say d equals 5. And that's kind of the answer to that one. So this guy is for that one. All right, let's take a look at this guy. So let's find the pattern. We got 10, 8, 6, 4, 2. Well, it looks like it's going down. So maybe we're not adding the same number, but we could say we're subtracting. -2, -2, -2, -2. And that's okay. If we're adding or subtracting the same number, it's still arithmetic. All right, still got that constant rate of change. So adding and subtracting is cool. We could also even write, if we wanted to, like +2, +2, +2, +2. So technically, we could still say we're adding the same number every time. We're just adding a -2. So this is actually arithmetic. But we say d is equal to -2, right? It's going down, so the common difference is actually negative on that one. Okay. This guy here doesn't have a constant rate of change. It doesn't have that common difference. Let's talk a little bit about that phrase common difference, right? Difference means subtract usually. So why are we using that subtraction if we're adding most of the time? It all has to do with how we find that number. So if you're like 2 + what equals 6, you're like, oh, it's 4. But sometimes with bigger numbers that gets hard. 18 + what equals 54? Well, in order to find out what that is, you would actually just subtract 54 from 18. So let's do that really quick. You probably do that in your head. But 54 minus 18, that's equal to 36. So by subtracting those numbers, I get what I need to add. So from 18 to 54, 18 plus 36 is 54 because 54 minus 18 is 36. So same thing here on the first one. This will probably make more sense. 22 minus 17, that's 5. Oh, so I'm adding 5. The subtraction is how you figure out what you're adding if you can't just see it right off the bat. 17 minus 12 is 5, right? 12 minus 7, oops, is 5. Okay, so that's why it's called the common difference. It kind of goes back to slope if you think about slope for a second. Slope is y2 minus y1 over x2 minus x1. So notice we take the second y and we subtract the first one, and that gives us the change in y, or the rise. Taking the second x and subtracting the one before it gives us the run. And so if you think about this as like y values, or these as y values or outputs, 22 minus 17 is 5. 17 minus 12 is 5. 12 minus 7 is 5. So that's kind of like your slope, but since we're talking about sequences, we don't say slope, we say common difference. Okay. So if we wanted to find the differences here, 2 plus what equals 6? Well, 2 plus 4 equals 6. But if you didn't know that, 6 minus 2 is 4. You could subtract, right? What's 18 minus 6? It's 12. That means I'm adding 12 here. So notice I'm not adding the same number every time. Now there is a pattern here. It's actually a multiply by 3 pattern. So I'm not adding the same number, but I am multiplying by the same number. Times 3, times 3, times 3, times 3, right? Okay, cool. There's a pattern, but that doesn't make it arithmetic. Arithmetic means the pattern is adding or subtracting the same number. And we can see that we're not. So although this does have a pattern and it is a sequence, it's not the special kind of sequence that we call arithmetic, right? It's not arithmetic. And so it doesn't have a common difference. We don't find a D for it. This is actually what we call a geometric sequence because the pattern is multiply. Don't have to worry about that right now, but for now we just want to know that it's not arithmetic. There's not an add or subtract pattern. Okay. All right. The next thing we might want to talk about is how to find a formula for an equation. Okay, let's go back to the pattern thing that we did, and let's talk about the equation that we found here. Right. So for this pattern, representing this pattern here, we said that we have this middle one, right? This middle one's the same every single time. So that's always there. And then you got like 4 sides. So here's the middle and here's the 4 sides, right? Here's the middle and here's the 4 sides. So what we determined is like, okay, we always have that plus 1 for the middle, right? That plus 1's always there. But then we're going to have 4 times the figure number. Because in figure 3, we got, 3, 3, 3, 3. For figure 2, we got 2, 2, 2, 2. For figure 1, we got 1, 1, 1, 1. So we take that number 3, there's 3 on each side, we multiply it by 4. And the equation we came up with is 4n plus 1. Okay? So for like a pattern, a lot of times we can represent it with an equation. And that's what we're going to try to do with these sequences. Okay? What I wanted to explain, though, is that since an arithmetic sequence is like a linear function, their equations look really, really similar. So this is a linear function. Okay, it's like, y equals mx plus b. I'm using function notation, so x is the input here. Input, right? So again, x is the input or the variable. M is the slope, and b is the y-intercept. Okay, what I want you to notice is that how similar these guys are. This is using function notation, this is using sequence notation. Here we have the y-intercept, but the y-intercept, remember, is like our starting point. It's where we start our graph. And a slope is like our constant rate of change. It's how much we're adding every single time. So if you had something like this, f of x equals 4x plus 1, you would say start at 1 and add 4 every time. Every time you go up, add 4. And so this is the add 4, add 4, add 4, and this is the starting point. Okay. An explicit formula for a sequence, it's a little bit different ordered, but it kind of has the same idea. The first term is your starting point. Okay, so this is basically, it's kind of like your y-intercept, right? Over here, you have a y-intercept. Over here, you have a first term. It's where you start. The only difference, though, is with linear functions, we start with 0. Your y-intercept is at 0, 1. But sequences don't start with 0. They start with 1. And we'll talk about how that makes a difference in just a second. But the main idea here is that your first term, A1, is basically like your B. It's your starting point, okay? Then you have your slope, right? Slope is m. It's your constant rate of change. Over here, your slope is not called slope, but we call it the common difference, but it's like the same idea. So m is a lot like d. And then we have a variable, x, right? That's the input. Well, here the input's n. So here you have an n right here. Now there's one extra piece, this -1, that's kind of weird. We need to talk about where that -1 is coming from. In order to do that, let's go back and look at our original pattern, our original linear pattern, okay? So our original sequence that we had from the pattern task looked like this. The first figure had 5 blocks, and then the second figure had 9 blocks, and the third figure had 13 blocks, and then the fourth figure had 17 blocks, right? Okay, now remember that we started with 1, 2, 3, 4. We start with term 1. So what I had you guys do, just to kind of make it easy for you for a second, is sometimes I had you add like the 0 step, right? So step 0. If we went backwards here, this would be 1. So it's adding 4 every time. 1 plus 4 is 5. 5 plus 9, 4 is 9. 9 plus 4 is 13. Okay. And so we kind of use this to help us out. But in sequences, we don't start from 0. We got to start from 1. So let's look at it in sequence form, and let's see what's going on here. Okay. A1 is equal to 5, right? The first term is equal to 5. Okay. A2, how do I get there? Well, I got to take 5 and I add 4 to it because that's the pattern, right? So A2 is equal to 5 plus 4. Now we know that's 9, but let's keep it in this form because this will help us for a second. Okay, A3. Okay, well, if I want A3 and I go back and think about what happened, I started out with 5 and then I added 4 and then I added 4 again. So A3 is the starting point and then I added 4 2 times. Okay, let's look at A4, the fourth term, this guy right here. How do you get to the fourth term? Well, you start with 5, the first term, and then you add 4 and add 4 and add 4. So this is 5 plus 4 plus 4 plus 4. Okay, let's do one more so we can see the pattern. The next one after this would be another add 4, right? Which would put us at 21. So A5, the fifth term, is 5 plus 4 plus 4 plus 4 plus 4. Okay, now this gets kind of tedious, right? You look at this and you're like, oh, that's annoying. I don't want to write plus 4 plus 4 plus 4. So we got to figure out a way to like shorten that basically to make it easier for ourselves. So let's think about the relationship here. At position 5, I've added 4 times. 1, 2, 3, 4. At position 4, I've added 4 3 times. At position 3, I've added 4 twice. So notice that the number of 4s I have is 1 less than this guy. Right? The number of 4s here is the number of 4s here is 1 less than this guy. Because I don't add 4 on the first one. I haven't added 4 yet. I only add 4 to get to the next one. All right, so that's kind of what's going on here. So if you think about it for a second, what about A sub 101? Sorry. I did it again. Okay, A101. There we go. If we want the 101st term, what would you do? Well, you have to start with 5, right? And then you'd add 4, add 4, add 4, add 4, add 4, add 4. But how many times would you add 4? You would add 4 1 less than this number, right? So you'd have to add 4, but you would add that 4 100 times. Okay? Let's go back and look at that pattern. This is 5 plus 4 times 1. This is 5 plus 4 times 2. This is 5 plus 4 times 3. This is 5 plus 4 times 4. Okay, so notice that I'm always multiplying by 4 because I have a group of 4s. I have repeated 4s. Okay, I always start with a 5. The 5's always there. What's changing is how many 4s I have. 1, 2, 3, 4. But this guy is 1 less than this one. So 2 is 1 less than 3. 3 is 1 less than 4. 4 is 1 less than 5. So the pattern here is you're adding a bunch of 4s. How many 4s should you add? Well, one less than the term number you're on. Right? At term 6, at space 6, you've only added 4, 1, 2, 3, 4, 5 times. One less than the position you're on. Okay? You could write this another way. I kind of am inconsistent with how I'm writing it, but A of 101, you could also write it 5 plus 4 times like 100, right? So you're still adding 4s, you're just adding 100 of them all at the same time. Okay? So let's say you wanted to write just a formula for any term, right? For any term that you want. So you write AN. This means any term number. You give me the term number and I'll tell you what the term is. Or you give me the position and I'll tell you what the term is. You always start with the first term. Like this sequence starts at 5. That's A1. And then you add to that a bunch of 4s. Okay? How many 4s do you add? Well, it depends. If you're at term 5, you add 4 of them. If you're at term 4, you add 3 of them. If you're at 3, you add 2 of them. If you're at 101, you add 100 of them. So if you're at n, you have to add 1 less than this number. And so what you do is you put n minus 1. Okay? This is the formula. Now, it looks a little different than the formula we came up with, but if you distribute this and combine like terms, you're going to get the same thing. This actually comes out to be 4n plus 1 if you simplify it. But again, the difference is sequences don't start with 0. They start with term 1. Okay, so let's take a look at this for a second. This guy is A1. This is D, my common difference. This is my input variable, n. The only reason I'm subtracting 1 is because I need this number right here to be 1 smaller than this number. Okay? So let's try this. What if we wanted to find A of 1001? The 1001st term. Well, I start with 5, and I add a bunch of 4s. How many 4s should I add? 1,000 minus 1. Or sorry, 1,001 minus 1, which would be 1,000. At position 1,001, I've only added 4 1,000 times. So this whole thing comes out to 4 times 1,000, 4,000, plus 5, so there's 4,000 plus 5, and that's just 4,005. So the number, the term, sitting in position 1,001 for this sequence is 4,005. We can jump all the way to know what the 1,001st term is just by using repeated multiplication. So let's go back and just look at this a second time, okay? This right here is like a template. You use this template to write a formula for a sequence. All you have to do is replace A1 with the first term of the sequence you're looking at, and replace D with the first term of the sequence you're looking at, and you're there. That's all you have to do. But just to kind of reiterate, this is the common difference. It's like the slope, and this is the first term, which is kind of like your y-intercept. So again, going back to this guy, if you were to look at this, and you're like, oh, my first term is 5. Cool. So A of n equals 5, my first term, plus common difference is 4. So I do n minus 1 times 4. There's your formula. So you don't have to go through this process every single time. This process was just to show to you or to prove to you that this template that I gave you actually works. Okay? So let's practice using it one more time. This will kind of be the last thing we're going to talk about here. All right, so I'm going to give you a new sequence. It's going to be arithmetic, and we're going to write a formula for it. So let's do this guy. Let's do 4, and then we'll do 7, and then we'll do 10, 13, 16, and dot, dot, dot. Okay? So what we want to do is we want to write an explicit formula. We want to write an equation, basically, for this sequence to represent this pattern. Okay? So we use this as a template. This is our template. All we got to do is take this thing, and we replace this guy and this guy. So let's write it out, and then let's replace what we need to. So the template for any arithmetic sequence, any linear looking sequence, is this. Start with the first term, and you add the common difference, n minus 1 times. Whatever that number is that you're looking for, you take 1 away. That's how many times you need to add that d, that common difference. Okay. So for this sequence here, this specific one, our equation is a(n) equals, we're going to replace this guy with the first term. So a1 means what's the first term? There it is. There's the first term, 4. Okay, we keep the n minus 1. That doesn't change. And then we replace d. So d is your common difference. And in this case, the pattern is plus 3, plus 3, plus 3, plus 3. So this is going to be a 3. Okay, so this right here is your explicit formula. All right, now let's use that explicit formula to find a term number. Let's find a term way out there. Okay, let's do the 51st term. Okay, a of 51. We're going to skip over all these other terms, right? This is term 1, term 2, term 3, term 4, term 5. Okay, we want to find the 51st, but we don't want to like fill in all the blanks. We want to jump all the way there. Okay, so if we want the 51st term, we have to start with 4, and we have to continue this pattern of adding 3. We're going to add 3, add 3, add 3. Okay, but how many 3's should we add? Well, at position 51, we need to add 50 3's, right? So what this is saying is, if this is 51, right, 51 right here, then what you do is you take that 51 and you subtract 1 from it. So 51 minus 1 is 50. Okay, so now you got 3 times 50, which is 150, plus 4. So this whole thing, A51, is equal to 154. Okay, so this is the explicit formula. You use this template, and you replace D with what the common difference is, and A1 with the first term for that sequence. And then you can use that formula, that equation, to be able to find terms that are way far off down the road. Right? 51st term, cool. It's 4 plus 50 times 3. Or 4 plus 51 minus 1, which is 50, times 3. And you get this guy. Okay? So that's the deal with arithmetic sequences. They're essentially linear. If you look at this guy right here, this is kind of like f of x equals b plus x times m. I know that's kind of backwards, but it's the same as a linear function, right? Slope-intercept form, y equals mx plus b. It's just that the order is a little bit different. So your slope and your common difference are kind of like the same thing. And your y-intercept and your first term are kind of like the same thing. The only difference is your first term starts at 1 and your y-intercept starts at 0. And then your input variable is x. Here your input variable is n. Again, since this sequence starts at 1 and not at 0, we don't start adding our common difference until we're on the second term. And so we have to, that's why we have that subtract 1. Okay. So if you need to, I would go back through the section 4.6 in your book and kind of get some more examples. Your homework is going to have a bunch of these types of problems on it, so you're going to need to know what an arithmetic sequence is, how to tell if a sequence is arithmetic, how to find a common difference, how to write an explicit formula, and once you know that, you should be pretty good. Thanks.